So today I'm going to look at a problem which is cylindrical coordinates. So there's no picture in the book in problem 352. I'll read it to you. A thin electrical heater is inserted between a long circular rod and a concentric tube. So the tube is shown here. Thermal conductivity, KB. The rod is in the middle. Thermal conductivity, Ka. The radius is R1 and R2. And we insert a thin electrical heater, the little red squiggly line, around the rod. Then the tube is outside of that. Then there's convection heat transfer on the outside. The air outside, minus 15 degrees C. Electric heater provides power. The heat from that heater goes through the material B and out to the air T infinity. That's how it gets out. We're asked to find the power required to keep the surface temperature at 5 degrees C. He kind of gives it away. He says, part A, determine electric power per unit length. Okay, so now we know what he wants, Q prime. Per unit length, that's Q prime. Okay, so we've got that in there, Q prime. Okay, watts per meter. All the energy generated by the heater eventually is going to get out to the air. So we can say for part A, Q naught prime is equal to all the heat generated by the heater is going to escape out by convection to the air. HAT surface minus T infinity. Okay, if I do the prime, the area of that is going to be, on the outside here, is going to be pi d, 2 pi r2, 2 pi r2 times L. Divide through by L, because that's what Q prime is. Divide through by L, 2 pi r2. That's the area per unit length. The area is 2 pi r2L divided by L. The area per unit length is 2 pi r2. H was given, 50. TS was given, 5. T infinity was given, minus 15. Do the calculations, pretty straightforward. You get 251 watts per meter. Okay, B. What's the temperature at the center of the cylinder? At center of the rod, which is right here. I want to know the temperature where the big black dot is. Okay, probably it helps to draw the equivalent thermal circuit, so I'll do that. We'll take the, let's go ahead and do it this way. Let's take the convection resistance here, 1 over H. Let's take the tube here, which is material B. Material B is LB, but divide by L. KB over, L over KA. So we have 1 over KA. Let's call this, I'm going to call that R. Make it simple there. I'm going to call that RB. This is RA. And this is, that's it, RA. Got it. Okay, and this is the center temperature. Okay. This is the outside temperature, T infinity. This is the surface temperature, Ts. I'll give this guy a name. This guy is the temperature where the heater is. Temperature of the heater. Okay. These are primes because they're per unit length primes. I'm supposed to find T at R equals 0. Okay. All the heat that comes into the thin circular electrical heater, it's like a piece of paper, you know, wrapped around a cylinder. So that's the electrical heater right there, okay? The pink. Inside of there is the rod, the solid rod. Outside is a tube. And the thin electrical heater is between the two. We found Q naught prime in part A. Okay, now comes the interesting part. On the diagram, show Q naught prime. Well, where did it come in? Between materials A and B. Oh, here and here. That's right. So there's Q naught prime. When it gets there, some goes to the right. Call it Q1 prime. Some goes to the left, Q2 prime. Q1 prime equals 0. Nothing goes right. Why not? Well, if it did go to the right, how's it going to get out of there? If the heat from the heater goes into material A, either material A gets hotter, okay, and if it does, it's not steady state, and this problem's steady state, we know that. So that temperature of material A is not allowed to change with time, steady state. Therefore, we know no heat can go in there. That's the key. No heat can go in there. All the heat goes out there. Heat comes in to TH and then makes a sharp left turn and goes out to T infinity. So TH is the same as T at R equals 0. Okay. And here's what we have then. Q naught prime equal the hot temperature, T of the heater, minus the cold temperature, T infinity, divided by the sum of the two resistors between my fingers, 1 over H plus RB prime, 1 over Ka material B, 1 over Ka material B. I know this, I know this, I know this, I know this. Solve for TH. And we get TH 23.5 degrees C. Okay, so I'm going to plot the temperature here's the temperature, hot temperature TH. Here's the cold temperature T infinity, not T infinity, TS. When you get to R equal R2, that's the outside surface, the temperature equal Ts, give it to me, 5 degrees C. This is 5 degrees C. T hot, 23.5 degrees C, that's up there. Remember, if it's cylindrical coordinates, temperature profile is logarithmic. Logarithmic. Okay. Starts up here, ends down here. A log type curve looks like that. Starts up here, ends down here. It's a log curve. It looks like that. Material A has to have the same temperature everywhere. Must have the same temperature everywhere. Flat across the middle. Okay. So there's the temperature profile as a function of radius. It's a little different than last time. We did one last time where the heat came in and it split left and right and went out those directions. Now, no heat can go in here because it has nowhere to get out. It's a dead end. Nowhere to get out. And it has to be steady state, so we know no heat can go in there. Otherwise, it would get hotter and hotter. Okay, any questions on that guy then?
Explain why it's flat out.
Yeah, because no heat can come in, so the temperature here is the same as it is here. If there's a difference in temperature, guess what happens? What drives conduction heat transfer? A difference in temperature. If you say I can't have Q, if I can't have Q, is K zero? No. Is A zero? No. Is L infinite? No. Oh, that must mean T2 must be T1. So if there's no heat transfer between here and here, what does that tell me about the temperature at these two big black dots? They must be the same. Any two big black dots. What's the difference in temperature between this one and this one? Because no heat transfer is allowed in there. That must mean that those two temperatures must be the same. Conclusion, these temperatures up here, all along here, for any radius from 0 to R1, must be the same. Oh, now you got a question, okay.
In the book and in some of the homework problems, they talk about contact surface resistance. Could you explain that a little bit?
I assign that one?
Yeah.
Don't do it.
Okay.
Okay, I'll tell you real quick. Contact means when you have two dissimilar materials and you press one against the other, it's never perfect contact. There is a resistance in there. And that resistance, okay, here's the asphalt outside on the street. Here's my shoe sole. Does my shoe sole everywhere touch the asphalt? No, the asphalt's rough to the feel. There's little bumps on it. Only place there's conduction is where the bumps touch each other. If you want, you could put a resistance in here to take that into account, called the contact resistance.
Okay.
You take a piece of sandpaper and a smooth aluminum surface. There's contact resistance because the sandpaper has little bumps on it.
Yeah.
And there's air in there. There's air in those bumps, between the bumps. So that gives you resistance. So you would normally include that, and in homework, all you do is add a resistance.
Okay.
But it's not going to be on an exam, just so you know. Okay, right. Okay. But that's what contact resistance, good point, thank you. That's what contact resistance means, yeah. So, if you have two really fine polished surfaces, ooh, very low contact resistance. Take a rough concrete surface like on freeway and a piece of sandpaper, oh, there's a big contact resistance because there's a lot of little trapped air in there, and that trapped air gives a resistance to conduction heat transfer. Okay, now we're going to go over to the last part of chapter 3, which is extended surfaces. Okay, let's look at the convection equation. T is minus T infinity. And we know that for convection, if we want good heat transfer by convection, we go to Newton's law of cooling, chapter 1. There it is. Okay. And somebody says to you, I want to make Q big. And they ask you, how should I do that? And you say, well, there's the equation. So let me think now. To make Q big, one thing I can do is I could make this term here big. How do I make that term big? Well, I make Ts big and T infinity small. So let's take the case of your automotive radiator. You're trying to cool hot water from the engine. How? By convection, of course, to the air under the hood. Okay, you say, well, okay, if I want to take more heat out of that hot engine water, coolant, I'm going to make Ts really big. And you say, okay, well, how do I do that? Well, you know, the hotter the stuff comes in, the hotter the surface is going to be. So I tell the engine guys, okay, guys, can you make the engine temperature of the water leaving really, really hot? The guy says, no, that's not the point. I'm trying to keep the engine cool. I can't make TH hot. Go back to your drawing board and try it again. The guy says, oh, okay. You know what? If I make T infinity really small, I'll get a big delta T. So in the orange manual it says, when you drive this new model, make sure you only drive it north of the 45th parallel in Alaska and northern Canada. Because I want the temperature to be really low. And the guy Palm Springs says, what? I can't do that. Okay, you get the point. You can't do that. You can't do that. The engine guy tells you what this is. This is what comes out of the engine, the water temperature. Live with it. This one's got to go all the way from Palm Springs, northern Africa, 125 degrees, down to northern, Alaska. I mean, from 125 down to minus who knows what up there. So you can't play with that. Too bad. And somebody says, well, if you make H really big, that's going to make that Q big. I'll take heat out of the water. I'll put this humongous fan. It blows at Mach 1 in front of the engine. Mach 1. I guarantee you, it'll take heat out. The problem is the car won't move. Too much power is going to this turbo fan. No, you can't play with that. You've got this little fan in front of your radiator. Behind it, okay? That's all you got. And it doesn't use much power. It doesn't use much power from the engine. So you don't want to take power out of the engine to drive that guy there. No. So, what are you left with? Area, you got it. That area, extended surfaces, here's what you say. Well, I'll take the water from the engine, and I'm going to put it through, let's say I never saw a radiator in my life, okay? I don't open the hood of my car, so I never saw a radiator. So I think, what's in there? Okay, probably a big fat tube, 6 inches in diameter from the engine. It comes down, goes down, and down. There's a fan in there. The guy'd be surprised. No. What's the surface area? I don't know, pi d times L. Not very much. So the guy says, you know what? I think I'm going to make more area, I'm going to make a lot of tubes like this and have the water come in all these tubes like this so that I get a bigger area. There'll be less flow here than that big tube. So I break the flow down in tubes like that. Good, you're on the right track. That's going to increase the area. Pi d times L times what? 1, 2, 3, 4, 5 times 15. Okay, H goes up. Another guy says, you know what? I could do more than that for you. I'm going to put flat pieces of metal, little strips of metal, between these tubes. And I'm going to call these fins. And boy, will that increase the area. Oh, you got that right. Try and count the fins in your automotive radiator. Try and count them sometime. It's like counting tree rings. Get a big magnifying glass. Oh my gosh, there's a lot of fins in there. That's a humongous area. So what do engineers do? Oh, they crank this guy here up. Everything we do to take heat out of something is that way. And, anything we want to take heat out of, or even sometimes put heat into, we make the area really big. So we call that bigger area extended surfaces. And one way we do that is by using fins. So fins are one way to make extended surfaces. So that's the history of why we use fins like that. because that's one thing we engineers can play with. Now the problem is, of course, when you add more fins and you add more tubes, you increase the weight, you increase the volume in the car that the thing takes up. So yeah, there's some play off there between the extra weight of the car, the volume it takes, the cost, and that's why, you know, we get paid the big bucks to try and optimize the heat loss from that particular engine. All right, let's draw a picture of a typical fin. It's going to be a very simple fin. It's called a rectangular fin. This we call the wall it's attached to. The temperature here is called TB. This stands for base temperature, the base of the fin. The fin is of length L. We're going to measure X from the base out to the fin tip. The fin itself, this particular fin, looks like this. There's a length, there's a width, and there's a thickness. A length, a width, and a thickness for this particular fin, called a rectangular profile fin. The fin is losing heat by convection. Let's assume the base is hot. It makes it more sensible to talk that way. So here's T infinity. The convection coefficient on the fin surface is H. The area when X equal L, that's called the fin tip, the tip of the fin. So there's a base of the fin, X equals 0. There's a tip of the fin, X equal L. What we want to do, find a differential equation that will allow us to calculate the temperature of the fin as a function of X. Okay, so what we do, we take a little differential element. Now what's it again? The temperature of the fin as a function of X. So we take a little differential element of dx in length. So there's our little differential element. That little differential element has a thickness of dx. Okay, and we show that, I'll show it down here. So here's the thin differential element dx. This is dx, this is w, and this is t. Now, energy balance. What comes in the left? Conduction in the x direction. What goes out the right-hand face? Conduction in the x direction. How about the top, the bottom, the front, and the back? Convection comes out. It's steady state. There's no generation. It's one-dimensional. It's constant properties. Those four assumptions. We're in Chapter 3. Those are the four assumptions in Chapter 3. Okay, energy balance says what comes in by conduction, Qx, must equal what goes out by conduction plus what goes out by convection. Of course, Qx is just based on our Fourier's law. Convection, Newton's law. But there's different areas. You got to be real careful. The areas in these fin problems require you to think a bit. For conduction, what area does the heat go through? It goes through that big area right there. Okay. So that's the conduction area, A sub C. The A right here is the convection area, perimeter times dx. They're different areas. Okay. What's the perimeter? In this particular problem, the perimeter of the fin is 2 times the quantity W plus T. 2 times the quantity W plus T. Take your finger, go all the way around. W, T, W, T. That's the perimeter. The area for our convection is this area here, plus the bottom, plus this area here, the front, plus the back side. That's the area for convection. Okay. We're not going to go through all the gory details. Put these guys in here. We've done it before. And go ahead and simplify the equation. And you end up with the governing differential equation. D squared T dx squared HP over KA. There's the governing differential equation. The reason why we don't put in for perimeter 2W plus 2T, or the cross-sectional area W times T, is because this derivation works for fins like this. It also works for a pin fin like this. Here's a pin fin attached to a wall. What's the perimeter? Pi times D. Okay. What's the conduction area? Pi r squared. Conduction area, slice it. What do you get? A circle. Conduction area, slice it. What do you get? There. Convection occurs where? Around the perimeter here, this area. Convection occurs where? Top, bottom, front, back, and maybe even that side. So we leave it general. Leave it general. Perimeter here, and leave A sub C in here. Don't put anything in until you get to a specific problem. Is it a pin fin? Is it a rectangular fin? A square fin? Leave it. It's general, so it can be used for any fins like that. That's not cleaned up enough for most math people. They want the equation to look very clean, like it's something they've seen before. So what they do is they do some things to it. They change a variable. They say, you know what? Let's let the new variable theta equal t minus t infinity. Then they say, I'm going to simplify some more. I'm going to let m squared equal the constant HP over KAC. And if I do that, I get d squared theta dx squared minus my m squared theta equals 0, whose solution, general solution, is theta as a function of x, then becomes equal to constant C1 e to the mx plus C2 e to the minus mx. So you can see how it cleans up the differential equation compared to the one over here. It may look like something that you solved before. So it cleans it up so it looks familiar. Now the new variable is theta. Don't forget theta is the temperature anywhere minus T infinity, T infinity, pardon me. T minus T infinity. Then you might say, well, I don't know, what would, why would someone call that constant m squared? Why doesn't it make more sense to call the constant m? Why say m squared? What kind of nonsense is that? Well, try it. All right, let the constant be m. Here's your solution. See if you like it. Oh gosh, no, I don't want a square root of m in that equation. I want it to be neat and clean. So what you say, you know what I'll do? I'll just make that squared, and this guy just disappears. Yeah, that's how they work. They want it to be neat and clean when they're done. So they call the constant m squared. Okay, now, to solve this guy, we need, of course, two boundary conditions there, with theta as a function of x. So BC number 1, take the easy one. At x equals 0, t equal tb. So, theta is equal to TB minus T infinity, and we call that theta B. Everything's in terms of theta. BC, number 2. We have 4 options, A, B, C, and D. There's more than that, but that's all we're going to consider. First one, convection at the fin tip. Don't forget the fin tip is the location, x equal L. Second one, adiabatic fin tip. Third one, a given temperature at the fin tip. The fourth one, we may be able to model the fin as being infinitely long. Only, you have to check this, only if m times L is greater than or equal to 2.65. We'll talk about that in just a minute. Okay, now those are the 4 possibilities at the tip of the fin out there. I'm going to draw those 4 cases on the board for you to show you how they look. I'll just put one here. We'll put them up here. This is case A. This is temperature T base. This is L X0. Okay, it's convection, so it looks like this. That's convection. That's how the fin temperature would vary with X. T infinity is down here somewhere. It's down there, low. Now I'll take case B. Same thing, X, L, 0, T base, T infinity. Comes down, now it's adiabatic, so the slope has to be 0 there. 0 slope. T infinity. Now I'll do a case C. X, L, 0. T base. T infinity. I tell you, the tip of the fin is kept at 100 degrees C. The tip of the fin is kept at 100 degrees C. I tell you, it's given, the temperature at the tip of the fin. Looks something like convection. They're very similar. And now I do case D. If the fin behaves as if it's infinitely long, well, an infinitely long fin, as it approaches infinity, guess what the temperature of the fin approaches? Oh yeah, of course. If the temperature of the fin, if the fin is very, very long, the temperature of the fin at the fin tip approaches, of course, T infinity, asymptotically. Comes down here, approaches it asymptotically like that. It approaches T infinity. Sometimes fins are like that. It's not very practical because you don't want to waste money by having a fin that's not losing much heat on the end of the fin, which this case does. It doesn't lose much heat at all because what's the difference in temperature TB minus T infinity? Oh, it's really small. You're wasting money for buying a fin like that. But it can happen. It can happen. So it's one of our cases. Okay, now we're going to go to, this thing's been solved now. For you, luckily, it's all been solved. This equation's been solved, the general solution, with these boundary conditions. Okay, so now we go to table, in your textbook, table 3-4. I'll just kind of outline what's on this table for you. Case A, B, C, D. This is the tip condition. Okay, you know, it's case A, convection. Case B, adiabatic. Case C, given temperature. Case D, infinite fin model. Okay, then we have the temperature distribution, theta over theta base. This column gives us the temperature distribution. This column gives us the heat transfer to or from the fin, QF, the fin heat rate. QF is called the fin heat rate. And then there's equations given here for all these guys. I'll give you an example. Table 3-4. Okay, table 3-3. Okay, I'll take the adiabatic. It's kind of easy. M times hyperbolic tangent ML. Adiabatic. M hyperbolic tangent ML. Now, at the bottom of the table, table 3-4, in the textbook, he tells you what capital M is. The square root, H, P, K, A, C, times theta B. The theta B is outside of the radical sign. Don't put it under the square root sign. Outside. Okay. If you want the temperature profile for that adiabatic fin tip, cosh M L minus X. Divided by cosh ML. Hyperbolic functions. If you want to, you can go to table B1, the back of the book. There they are. Hyperbolic sine, hyperbolic cosine, hyperbolic tangent, table B1. You'll have that table on the first midterm. But, yeah, let me show. Have you used it before?
Yeah.
Okay. Of course, who wants to interpolate tables on an exam? That's no fun. So, probably you use this, okay? You'll use this. You can't use your smartphone, so if you haven't practiced, practice with this, you know. All the TIs have it, so.
You gotta go to the directory to get it.
Do you?
Yeah.
I'm an HP guy. Mine's already on there.
Okay.
Okay. So yeah, I would, you know, if there's a problem that requires you to find hyperbolic functions, I'd use your handheld calculator. But you will have table B1 on the exams, the midterm and the final, in case you need it. Okay. So this table is titled Fins of a Uniform Cross-Sectional Area. Okay. This is what it means. It means if you slice the fin normal to the x-axis, here's the fin coming out of the wall. If you slice the fin normal to the x-axis, get a knife, slice through, slice through, slice through, the area here will not change as x goes from 0 to L. If you take a pin fin, x is that way, slice normal to the x direction, circle, 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 circle. It didn't change. That's called a uniform cross-section. But now, if you've got a triangular type pin fin that looks like this, attached to a wall, oh no, don't go to table 3-4. Now when you slice it, normal to the x direction, the area gets smaller and smaller as x increases. So you wouldn't use that table for that fin. So that's what it means when they say uniform cross-sectional area. How does the area change with x? Okay, now, any questions on that before you go on? Okay, now another way we engineers analyze fins is we talk about and we calculate the fin efficiency, how efficient the fin is. There's different ways to calculate how good a fin is. The fin effectiveness, our textbook talks about that. The fin efficiency, our textbook talks about that. We're not going to be concerned with fin effectiveness in the textbook, so you can eliminate that from reading. It's going to be fin effectiveness, okay? Fin efficiency, pardon me. So fin efficiency is what we're going to analyze. Let's put that up here. Okay. It's given a symbol, eta sub f. Here's how it's defined. The actual fin heat transfer divided by the maximum fin heat transfer. And we define the maximum fin heat transfer would be the heat transfer if the fin temperature was everywhere T base. The fin would lose the most heat if the temperature of the fin was everywhere at that hot temperature of T base. So that's the definition of fin efficiency. In symbolic terms, it's QF, maximum fin heat transfer, HAF T base minus T infinity. That's the maximum heat transfer from the fin, if the temperature were everywhere at the base temperature. Okay, now, we're going to look at how it's presented. The first way it's presented is on a graph, figure 319. Figure 319 gives you fin efficiency in percent versus an x-axis variable, which is rather lengthy. The textbook goes through why that's important, but we're going to use it. Say, well, how'd they come up with that thing? L sub c to the 3/2 quantity h over k, p to the 1/2. It's described in the textbook. But that's the x parameter we're going to use to find the fin efficiency. It looks something like this. Of course, the efficiency goes down as we get the length longer. Okay, let's talk about the variables in there. We know what h is, we know what k is, we know, okay, let's look at L sub c. I'll put that over here, I think. Let's put over here. This is how this fin looks. There's a picture in the textbook on the figure so you don't get confused. He tells you, next to that little graphic, he says, L sub C is L, this is L sub C, L plus T over 2. T is the thickness. All these things are on the figure, so you can have it right in front of you there. He says, A sub P equal L sub C times T. Okay, so now you can find the X parameter if you know the length, the thickness, the K, the H. Then there's another graph on there, another line on that graph, which looks like this. This is for a triangular fin. This is L, this is T, and on the graph he tells you L sub C equal L, A sub P equal L times T divided by 2, the area of the right triangle, pardon me. 1/2 base times height. Okay, now let's talk about what each of those things mean. A sub P stands for profile area. The profile area is the area you see looking at this picture. This area here, the profile area, is the base, L sub C, times the height, T. Okay, there it is. This is a triangle. In a profile view, the area is 1/2 the base, L, times the height, T. L sub C is L, down here. L sub C, L plus T over 2. Why? Okay, here's the difference. This is the actual fin. The actual fin is losing heat by convection out of all these areas. All the areas where the arrow is. The length of that fin is the actual fin length. That's the actual problem you've got. But when you consider L sub C, what they're saying is, well, what if we design a fin which loses the same amount of heat, but the tip of the fin is adiabatic? We'd have to make the fin longer. Now this is adiabatic. No heat gets out of there. But we still have convection on the sides. The length of that fin we call the corrected fin length. L sub C stands for corrected fin length. So they present the results on that graph in terms of L sub C. And what is L sub C? It's the length of the fin so that both heat transfers are the same. Q fin here and Q fin here are the same. Make Q the same. Therefore, if the fin tip is adiabatic, you must make the sides of the fin longer to lose heat by convection. Okay, just so you know what that means. Corrected fin length. Why isn't it up here? Well, guess what the area is when x equal L? Well, I'll tell you, it's 0. Okay, so you don't have to correct anything because there's no heat loss from the tip of the fin. Is there heat loss from the tip of the fin here? Oh, yeah. Therefore, you correct it. Is there heat loss from the tip of the fin here? Oh, no. So you don't correct it. You don't correct it. Question back there?
Is that because, like, the radiators and the
Oh, yeah. You're thinking about this case. That's a very good case. Here's 2 walls, the same temperature. There's a fin. Guess what happens in the middle of the fin? How much heat crosses that line? I'll tell you, you know, nothing, right? It's symmetrical. If this is 100 degrees C, that's 100 degrees C. Guess how much heat crosses the middle of that fin? Nothing. So that fin right there is which case? There it is. Adiabatic. Adiabatic. And how much heat does that fin lose? 2 times the heat that fin loses. 2 times the heat that fin loses. That's right. So We don't put insulators on tips of fins. No, nobody does that. See, so where would you use case B? Okay, I'm showing you right now. Your automotive radiator, right? Your automotive radiator, between the two pipes carrying hot water, there's a flat fin. We engineers model that by case B. Yeah, good question. Okay, back to here. So we can get A to F here. Okay, figure 320. Now we have fins like are attached to motorcycle cylinders. Okay? They're round fin, called circular fins. So they look something like this. Oh, for sure they're fins. They're attached to tubes. Sometimes they're attached to like the cylinder of an engine. So there are your circular fins. And the, I'll draw a picture here. So here is R1, here's R2, this is the fin. The tube it's attached to is outside radius R1. Okay, we're going to plot the fin efficiency here, 100%. The x-axis parameter variable is L sub C, same thing like the previous one. There are different graphs now, different lines on the same graph. Each line has a different value of R2C over R1. On the graph, he tells you, he says R2C is called the corrected fin radius. R2 plus T over 2. He tells you on the graph that AP is equal to LC times T. On the graph, he tells you that L sub C is L plus T over 2. So all that information is on the graph. Same principle as over here with the rectangular fin. What the corrected fin length means. It means the same thing on figure 320 as it means on figure 319. Okay, now those guys, it's hard to put graphs on computer codes. So what's on here is also in table 3.5. Table 3.5, let's put that right here. Gives you the fin efficiencies of different geometries. For instance, in equation form. For instance, well, there's straight fins, circular fins, pin fins. Straight fins, like we looked at over there on the right left-hand panel. And then they give you the equation. They give you lots of fins on that table. 1, 2, 3, 4, 5, 6, 7. There's 7 on that table. I've shown you 2. There's 3 straight fins, 1 circular fin, 1 pin fin, 1 parabolic fin, 1 triangular fin. They're all on table 3.5 in equation form. So you have a choice of using table 3.5 or the graphs 319 and 320, because circular fins are here and they're here. These fins are here, straight fins. Are there triangular fins? They're over here too. 2 places to find them. Yeah.
So the fin efficiency is the same formula for pin and straight?
Mm-hmm. but the M's different, and things like that.
Okay.
Yeah, because they both come out from a wall, and they both have uniform cross-sectional areas. Yeah, that's why. Now, when you use figure 319, 320, or table 3.5, when you use that, you're going to get an efficiency. So from that, how do you then get what you want, which is what you want, is a heat transfer, obviously. You want the heat transfer. The fin efficiency is nice to know, but the main thing is you, the engineer, want the heat transfer. Here it is. If you want the fin heat transfer, take that fin efficiency from that, either the figures or the table, and multiply it by the denominator. There's the answer. There's going to be more areas, but I'm telling you right now there are 3, and you have to know what the 3 areas are. Number 1, there is, I think I erased it already, there's an A sub C. A sub C stands for cross-sectional area. There's an A sub P in the graphs. It stands for profile area. There's an A sub F in the heat transfer equation. That stands for the area exposed to the fluid, which might mean touching the air. If this is a pin fin on a wall, and what is AF? Pi d L sub C. Pi d L sub C. What's A sub C? Pi r squared. What's A sub P? L times 2 times the radius, or L times the diameter. Oh yeah, they're all different, and it's easy to make a mistake on that, believe me. Okay, we're going to work some problems next time using these 3 approaches, so I think we'll stop here for today. So we'll see you then on